Okay, so we can start actually. So good evening again in this week 4 session of Basics of Semiconductor Microwave Devices. Uh, so I'm Shahzan Bhatt. I'm a direct PhD at Applied Quantum Mechanics Lab at IIT Bombay, and the course instructor is Professor Digvijay Nath of IIC Bangalore from Sense Department. So we are right today going to cover basics of 3.5 MESFETs, which are quite intriguing devices. Apart from the MOSFETs you might have studied in the previous basic device physics course, but MESFET is a little bit different in certain aspects and a little bit, I should say, same in some aspects if we talk about the device physics of these MESFETs. So what we are going to cover today is something like this. We have covered in week one, we have covered some introductory physics about the RF devices. Then we have covered the heterojunction physics in week two. Then we have talked about TEDs, which are transfer electron devices, high power, high frequency devices used as, let's say, oscillators or to deliver high power. We have talked about the impact diodes, avalanche diodes, and the gun diodes also, which are maybe tunnel diodes we have talked about, which are based upon some quantum tunneling based effects, which give rise to negative resistance. So negative resistance we have talked about in the previous session. We have talked about something like IV curve looking like something like this. Then this is the region where we want the amplification of the signal, which is the negative resistance of negative resistance of these particular devices is utilized in order to get the, I should say, amplification of the microwave signal. So, and this particular negative resistance curve arises due to different effects in the tunnel diode we talked about. In tunnel diode, we talked about quantum tunneling effect. In, let's say, gun diode, we talked about another effect, which is the gun effect. And in this diode, it's special because there is no junction in this diode. It's a bulk material showing this particular effect, and particularly, let's say, gallium arsenide, where you have those in the EK diagram, you have those valleys in which are called basically as satellite valleys, where the electron has different effective masses. So electron can go here, and the effective mass is different. That means the mobility will be different, and the current is going to be different. And as a result, we get a dip in the current. Okay. And the tunnel diode is because of the quantum tunneling effect. If you have a quantum tunneling going on, you have a very high doped P plus region and N plus region. The electrons can basically tunnel to the other end of this system. But if you apply the bias to this particular system, particularly the reverse bias, then what is going to happen is that these two states will be separated, and the tunneling will no longer occur. So that's going to create the negative resistance states. So these are two different devices with two different physics, but having the same effect on the microwave signal. That is, they are going to amplify the microwave signal in this negative resistance region. Okay, so that was what we covered. Now, today, what we are going to cover is something called as 3-5 FETs, which are 3-5 field effect transistors. Their physics, their IV characteristics, certain maybe some basic equations, and some questions which will be today solved in between the slides and not at the end of the particular this session. So I may have pasted some of these questions in between the session. So that's why it will be necessary for you to watch the entire lecture in order to check where I have solved those questions. Probably they will be solved just after their particular topic will be discussed. So prior to that, we will discuss some of the topics, and then we will solve a question which will be from the similar topic in the assignment session section. So now what we are going to do is that we are going to cover it. Now, first of all, we know about from the basics of, let's say, MOSFETs. You know about MOSFETs. But before that, you know about something called as MOS structures, which is metal oxide semiconductor structures. Metal oxide semiconductor structure. Just a brief overview in 10-15 minutes. What you have studied till now. So you know that if you have a stack like this, you have a metal, you have an oxide, and then you have a semiconductor. Let's say this is a p-type semiconductor, and we're talking about a silicon, what we have studied till now in the silicon based FETs. And let's say this is an oxide, let's say this is an oxide insulator, and this is metal. Then you know about MOS electrostatics. What is going to happen is that You apply certain voltage here at this particular terminal, let's say because of the field effect. Field effect means there will be, let's say, positive charges here, there will be electrons present here because of the field generated by from the metallic plate. Okay, so there will be electric field lines in this direction, so that is going to control this particular channel, which is basically beneath this particular oxide layer. So that is the simple MOS capacitor. It is just used to test the devices to compute their capacitances. The current doesn't flow in this particular device because there is no source and drain region. Okay, so this is the simple MOS capacitor. And also you know that apart from this DC voltage, which is VG, let's call it VG, if you have some small signal voltage, let's call it small Vg over it, then you can actually swing that voltage in order to compute what is the frequency response of this device, how are the carriers going to respond. And similarly, you have certain three regions. You have accumulation region, you have depletion region, you have inversion region in this particular, where these three regions are differentiated based on what type of carriers are present in this region, in this channel. So that represents what these three regions are. In the accumulation, it will be majority carriers. If it is p-type, it will be holes. In the depletion, it will be the channel will be basically depleted, so there will be depletion region formed. If it is p-type, then it will be some plus depletion regions, maybe. Or maybe if it's like this, if you rotate the device, if you have a metal, you have an oxide, you have a semiconductor, then you have an oxide in between with a very huge band gap. And in on the semiconductor side, you have maybe a semiconductor like this, which is a p-type. So this is conduction band, this is Fermi level, this is valence band. And on the metal side, you have a Fermi level, which is like this, metallic Fermi level. Okay, so then you might have certain band bending like this in this particular system. That is what you have studied till now. And in equilibrium, your Fermi level will be aligned. That means there will be a common Fermi level throughout. This is the Fermi level, and this is the conduction band, this is the valence band. Okay, so that's what you have studied till now. And depending upon, let's say, if you have an inversion happening, then you will be having charges which are opposite to semiconductor type. That means if it's p-type, then the inversion charges will be electrons. So that's what you have studied. That means you might have electrons here. That means this particular surface is inverted, and particularly the onset of inversion, you know that this conduction band goes below the Fermi level. Okay, so that means there's a huge concentration of electrons in here. So that is the fundamental physics we have discussed about in the previous sessions of device physics prerequisite. Okay, so now then what you have done, you might have done is that you take this MOS capacitor, and you take this MOS capacitor just like here, and you attach the source and drain regions. If it's a p-type substrate, then the source and drain regions will be highly doped N plus regions. If it's an n-type substrate, then the source and drain regions will be p-type, highly doped p-types pockets. Okay, these are called as pockets. Okay, so then you have an oxide here, then you have a gate stack here. You have a gate, which is a metallic gate. So this is just a front view. This is just the front view of the device, a cross section of the device. In actual representation, it looks something like this in the three-dimensional view. But since every section of it, let's say if you cut one section of it, that will be similar to other section, that will be similar to one more section. So it doesn't matter whether you study the front section or the middle section or the back section. The physics is going to be similar. Okay, that's why you study it in two-dimensional system. Okay, so now that you have studied, what you have studied in this particular system is you have studied that if you apply, let's say, a certain gate voltage at this particular end, let's say you apply a very high positive gate voltage, a gate voltage greater than the threshold voltage. Threshold voltage is the voltage which actually inverts the channel. Okay, so this inverts the channel. That means it brings electrons near the channel, a huge density of sheet charge of electrons. Okay, so it brings these electrons near the channel, and then you apply certain voltage on the drain. You apply, let's say, a positive voltage or a negative voltage on the drain. Let's apply positive. It doesn't matter because it's a symmetric device. If you apply positive voltage, if you apply negative, ground this particular thing, you ground this particular terminal, and you ground this particular terminal also. This is positive and this is negative and this is grounded. This is negative. So what is going to happen is that now this drain terminal is positive. The electrons are going to flow in this direction and you will have current flow in this direction. So this is the current flow, this is the electron flow, and the current flow is opposite to that of the conventional electron flow. So this is the conventional MOSFET, which is the metal oxide semiconductor. So there is an oxide present here, this oxide. And the one of the significant difference here is that you have to induce this channel. This channel was not present before. If you don't have gate voltage greater than threshold voltage, there will be no channel in these devices. No channel. So that is what this particular device is called as enhancement type device. This is called as enhancement type device. Why? Because you have to enhance the channel. Channel means this conducting pathway, you have to make it by applying certain voltage. It's not already there. Now, jumping into the MESFETs, what is so intriguing about MESFETs is that they are mostly depletion type devices, and you don't have any oxide between the gate and the drain. There is something called a Schottky barrier formed. Okay, and one more thing you might have studied here, you might be knowing from your previous studies is that this is basically a diode. This is basically a diode, so these are connected and they are all grounded. Okay, so you want these diodes to be reverse biased so that the current should not flow in that particular direction. Okay, so that is the reason the current basically likes to flow in this region. It does not go towards this region. Okay, so there are different considerations what you might have studied, and from the MOSFET, if you have N plus regions, this is oxide and this is gate. You know that there is a depletion charge present here. This is depletion charge. It will be slightly in the towards the N plus region because it's heavily doped, and it will be mostly penetrating towards the P substrate, which is this. So that means it's a PN junction, where this is the depletion width. What you have studied in the PN junction. Similarly, on this side, this will be positive ions. This will be negative depletion region, negative depletion region. It will be spread towards the P-type substrate. So this entirely is basically the depletion region. So there is basically depletion region up to here. So this is the huge depletion region. And then apart from it, there are electrons which are induced by the gate in the channel. So you see that it's a quite of messed up situation in between here. There is depletion charges also. There are electrons, free electrons also. And you can change this scenario by applying different gate voltages, by applying different drain voltages. Okay, you can change it altogether, because if you apply, let's say, a positive voltage here, you apply a positive voltage here and ground this thing totally, then that means this particular diode, what is it getting? This is N plus is connected to the positive, negative is connected to the P. That means it's reverse biased. Okay, so in the reverse bias, you know that the depletion width increases. If you have a PN junction, Pn, this is plus, 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 minus, minus, minus. And if you reverse bias this junction, this depletion width is going to increase. There will be no conduction. Okay, so this depletion width will increase. So that's what exactly happens here also. This depletion width increases. I'm talking about MOSFET. So physics is similar. If you have understood diodes, then you can extrapolate the physics of the diode to understand all the devices. Now this is the conventional MOSFET, what you have studied. Now what is so different about MESFET? Okay, so the different thing is that these are depletion mode devices. Depletion mode devices. What is a depletion mode device? Depletion mode device, the channel is already there. You just have to make sure you are removing the channel. Channel already there. That means those electrons which we had to induce here, these particular electrons, these were induced by the gate terminal. Okay, these were not there. In here, this particular channel is already having electrons. If this is let's say N plus region, this is N plus, this is, let's say, a gate terminal directly over the substrate. Let's say this is N type gallium arsenide, or let's say this is maybe gallium arsenide or gallium nitride. It doesn't matter. So these electrons are already there. So what you have to do, that means it's normally on. But what you are going to do now is that you want to control these electrons. So that is why gate terminal is there. Gate terminal acts like a controlling terminal to these electrons. Okay. Otherwise, if you just connect these two terminals, if you just apply a positive terminal here, negative terminal here, ground this thing, you will see that the current will start to flow. Okay, the electrons will flow in this direction, current will flow in this direction. This is the current direction. That is the main difference between enhanced and depletion type devices. And these particular devices are mostly depletion mode devices. Okay, these are depletion mode devices. So don't get confused what is happening. If you have studied these lectures of professor, don't get confused that why is everything happening in the opposite. Let's say if you have normal MOSFETs, which are whatever you have studied till now are enhancement mode MOSFETs. And if you talk about MESFETs based on, let's say, 3 5 devices, these are mostly depletion mode MOSFETs, depletion mode FETs, field effect transistors. So in here, you might have seen the IV characteristic, which is the output characteristic. Output characteristics means output current, which is in, let's say, milliamps, versus the output voltage, which is drain to source voltage. Okay. So you might have seen something like this. Increases, then it saturates, increases, saturates, increases, saturates. Okay. So this is for different, let's say, VG1, VG2, VG3. So this is for one gate voltage, then you increase the gate voltage, then you increase the gate voltage. Okay, so VG increases in this direction. So let's say this is maybe 1 volt or maybe zero point 0.1, let's say 0.2, 0.3. You might have seen a trend like this if it's a P-type substrate. If the MOSFET is having a P-type substrate, you might have seen the current voltage characteristics like this. Okay, wherein you have a region up to this point where it's a linear region, the current increases linearly. That means it's just like a resistor. It's an ohmic region. Okay, because I equals to V equals to IR type relation. Okay, but then here in this particular region, the current saturates. So it's a saturation region. Saturation region. So you will see that this particular saturation region is useful for microwave devices. Okay, why it's useful, that's what we are going to study today. But this is enhancement mode, what you have seen. In the depletion mode, the IV characteristic also looks similar. You have the ID, let's say in some milliamps, and you have VDS, and you draw it something like this. Okay, you draw it something like this. Okay, then you see that this particular first one is for VG equals to, let's say, minus 2 volt, VG equals to minus 1 volt, VG equals to, let's say, 0 volt. You see that what is happening is that as you are increasing the gate voltage in the negative direction, the ID is reducing. Okay, so this is for 0 VG, this is for minus 1 VG, this is for minus 2 VG. That means if you are applying the more and more negative voltage on the gate, you are depleting the channel. You are removing those electrons. You are removing these electrons, which are present here. You are removing these electrons from now here. Okay, because if you have this structure as a MESFET, this is N plus, N plus, this is, let's say, N gas. So these electrons here, you have a gate, you are applying negative. Negative is repelling those electrons in a basic sense. So that means you're depleting it. You're bringing it more towards the bottom end. That means the depletion region goes like this. Okay, this is the direction of the depletion region. What should I call depletion region? It's actually getting depleted of electrons. It's getting less number of electrons now there because you have applied negative voltage. So that's why when you are increasing the negative voltage in this direction, the drain to source current is reducing in it. So that means you have this is source, this is source, you have grounded it, and this is drain. You have entered, you have applied a positive voltage at the drain, and then you see that the drain current basically reduces. Okay, so that's why you're trying to turn it basically off. Otherwise, it was already on. At Vg equals to zero, it was on. So that is the basic difference between the depletion and the enhancement type devices. And now what we are going to do is that now marks the beginning of what is basically happening in these devices. So you see in these particular devices, the working is quite similar. You have the gate voltage, then you have the negative VG. Negative VG suppresses the current, it suppresses the current. A large negative VGS, it turns the device off. Okay, so initially you might have current something like this in the linear region, then it decreases, then it becomes zero, because you had the electrons here, you want to repel those electrons towards the bottom end, and you want to make it free of electrons. Okay, You don't want now the channel to be there in order to turn it off, because you just have to turn it on and off, on and off. And now electrons go down, electrons go away from this region, and then this entire region gets depleted of electrons. Okay, and you have the device turned off. And you have something called as pinch off voltage. Pinch off voltage is where the voltage at which entire region is covered with the depletion region. Okay, so that this is the particular pinch off, the voltage at which, let's say, if VGS equals to pinch off voltage, then entire region gets depleted. So you have a depletion in entire region. This is not the pinch off voltage what you have studied in the MOSFETs. So in MOSFETs you have a pinch off concept, something like if you have a channel, if you have this channel of electrons, then if you as you increase the drain to source bias, the channel looks something like this, it looks something like this. Okay, then you have these particular regions which are called as pinch off regions. This is pinch off region in what do we call as MOSFETs. Okay, but here you have the entire region to be converted into the depletion region, because first of all there is basically a direct connection of the gate toward to the substrate. There is no barrier in present. There is no oxide barrier. So basically, if you zoom this region, how does it look? If you have a gate and then you have, let's say, N gas, N-type gallium arsenide, how does the energy band diagram look like? You have the Fermi level of the gate, which is this, and then you have the barrier, Schottky barrier, which looks something like this. This is the conduction band of gas, this is valence band of gas, this is Fermi level of the gas, and you have some surface states here, which are defects, surface or defect states. Let's call them defect states. That creates something called as Fermi level pinning. It pins the Fermi level at that place. Okay, it doesn't move a lot, and this barrier is called as Schottky barrier, and this height is called as built-in voltage of a Schottky diode. And then you can find this particular voltage, which is basically EC minus EF. It's basically can be found out by phi B minus, let's say, VBI. Okay, approximately. Then you can basically, not exactly from this, but you can compute this particular EC minus EF is, that it's KT by Q ln of NC over ND, if this particular thing is doped with
Bhaiya, I
ND.
have a doubt
Okay,
here
then you
in
have
this
all of the
diagram.
scenarios. What is happening in the Schottky diode? You apply a If you
Hello,
apply negative here, if you apply a positive voltage here, then you have the maybe electron trying to go in this direction, but it won't be able to go because there's a barrier. Then the scenario can happen that electron can tunnel and appear on the other side at a very large bias. And that happens in these type of devices. If you apply very large negative voltage, you will see that the leakage will start to happen. That means the electron from the gate will start to enter into the channel, and that is a degradation of the device. Okay, so now this was a linear region. So this particular thing was linear region. This is
hello,
for linear region. Okay,
hello,
now what happens is that if you talk about, yeah, we can take the questions at the end. What's your name? Ketavant Hemant. We can take the questions at the end.
Like I
And
have a
then
question
if
in
you
the
have a
diagram.
saturation region now, because the current is not going to keep on increasing till infinity. Okay, then what happens is that the current starts to saturate. You have if you go on increasing the what should I call that, drain voltage, VDS, then you see that depletion region now shifts towards the drain voltage. That's what happens here. Okay, it starts to shift towards this particular drain region, because now you have applied, let's say this particular was negative, and then you started to apply the positive. You started to apply the positive, and positive drain voltage increases, and you start to apply more positive voltage towards the drain region. And that means this particular point gets shifted towards the drain region. It's just like if you draw the diagram of it, it's just like the drain is bringing the positive voltage, lowers the electrostatic potential of the electrons. Okay, so it just like that, it brings this particular barrier down. If you have the What happens in a MOSFET? You know that if you have a MOSFET, if you draw it here, let me bring a page. If you have a MOSFET, if you have a MOSFET, then if this is a oxide, this is gate, this is gate, then how do you draw the electron band profile from in this direction? If you go from this direction, if this is source, this is drain. This is source, then in between there is a barrier and there is a drain. Okay, this is the band profile. This is the valence band. And same you can do it for the conduction band. This is the conduction band. And if this is n-type, then the Fermi level is closer here, then the Fermi level is closer on the other side, which is the drain. So this is source, this is drain, and in between you have this particular region. Let's say if it is P region, then it will be closer to the conduction band. There is no band in the Fermi level. Fermi level is flat. Okay. So what does gate do? If you apply gate, if you connect a gate here, and if you apply positive at the gate, so the positive is lowering the electrostatic barrier for the electrons. That means it brings this green barrier down, something like this. And then you have the electron population that goes in this direction. What is the question? So in that band diagram, whether metal electrode Fermi level won't cross the barrier. Which band diagram? Whether metal Fermi level won't cross the barrier. Which diagram are you talking about? Are you talking about the band diagram of a Schottky barrier?
Yes,
Okay,
sir.
Schottky barrier. What you are saying is that if this is the common Fermi level, this is the Fermi level of metal, this is the Fermi level of this, and you have a bending something like this, something like this. So you're saying whether the metal electrode Fermi level won't cross the barrier. What does it mean the Fermi level cross the barrier? It doesn't make sense.
Yeah.
I think you're talking about
By
the electrons,
hello.
right? You're not talking about the Fermi level. The Fermi level will be in equilibrium, it will be flat and it's closer to this particular region. That means this is n-type. And the Fermi level is flat throughout. That means it's an equilibrium case. Now, yeah, you can raise. You can apply let's say a negative voltage here. If you apply a negative voltage here, if you apply a positive voltage here, this Fermi level will go up. So it will be now split. There will be Fermi level. There will be different Fermi level here. There will be different Fermi level here. It will be splitted. Okay. So that's what I'm telling you. Now, if you have an electron here, it has it has two chances to go. Either it can go over the barrier, something called as thermionic emission, or it can tunnel if the barrier is low, then appear on this particular side. Okay, so that can control this particular something called as this, if this is EF1, this is EF2, then EF1 minus EF2 will be basically applied voltage. Applied voltage. So yes, you can do it. That is what happens in the device. The applied voltage creates basically the difference of the Fermi levels, okay, on the two sides of the device. If it is P and N type, then you split the Fermi level. But yeah, this is what happens. This is how mostly the conduction takes place. Okay, but mostly these are if you have let's say if you apply a positive on this side now, if you apply a negative on this side now, this will bring it down. It will lower the barrier and the electron can go via the thermionic emission route. So that is the mostly how the conduction takes place. So because if you have an electron here and if you have applied negative here, the electron cannot go through this. Okay, this is the barrier, huge barrier for the electron, this particular thing. Okay, but for the holes, it's not a barrier. This particular thing, it's not a barrier for holes. That means if you have a hole here, hole can go through this. So that's why if you have there are certain usage applications where you can use it for a motion movement of the one type of carriers. Rather, you can control the conduction band of uh, conduction band. I should say if this is conduction band, this is valence band. Then basically you can control the either the valence band or the conduction band. But I don't want to confuse you guys because it's a little bit involved concept. Okay, so that is the
Sir,
basic
in that
fundamental of
case,
it.
we
So I
can.
was talking about this particular device. What happens
Yeah.
is that you apply the gate and you bring the barrier down so that you start the conduction. Okay. So now if you apply a voltage here at the drain, earlier only gate was present. Now if you apply a drain voltage which is positive, what happens to these barrier? Now I draw with pink line. So this remains same, but this starts to dip. This remains same, but this starts to dip. Okay, so that's why then you see if there are electrons here, electrons will go down this. Okay, So that is the actual conduction mechanism that happens in the MOSFET. And a similar thing, but if you apply a drain voltage huge enough, that creates this band bending, and that creates this particular profile, this particular region where you have a huge band bending. So there is a region with the huge band bending, where if there is an electron present here, if there is if there is electron present here, let's say this is drain end, if there is electron present here, it will go down the hill. Okay, and this particular region is basically where the velocity basically can reach the something called as saturation velocity, because you know that this particular bending in the conduction band, it's basically related to something like, if you have a electric field E as a function of x, you can write it as minus 1 over q dEc by dx. That means there is basically a field present at that particular point, which is basically equivalent to minus 1 over q, the slope of this particular conduction band. So that means you have a field, and that, let's say the field direction is in this direction. That means the electron will go down the hill, and down the hill, because it's a very steep slope, it can cause other effects also. Let's say it can cause impact ionization, which we have discussed in the previous section. Because of huge kinetic energy, it will hit other atoms, knock out electrons. One electron will hit, it will give two electrons. This will give four electrons, so on and so forth, and the cascade reaction can happen, and you have certain breakdown mechanisms. But there are other mechanisms how you can tackle those regions. Okay, so this particular length is going to be very, very important. The length from this point to the drain point is going to be very important, because you saw in the previous week, you also saw that how you can tackle the breakdown is that you can control this length, this particular length. If you can control this length, then you can control the breakdown. You won't allow this cascade chain reaction of the electrons hitting other electrons to pass away. You can, let's say, maybe it can, maybe up to go, one electron can produce two, two can produce four, four can produce eight, and then it will stop. Let's say you have made the length of this particular region up to this point, then it will stop. That means the length is going to be a very important parameter in deciding the breakdown voltage and other things of this particular device. So okay, so remember this thing, because this will be, I guess, it will be important for one of the questions in this. So now we have one of the questions. What is the question? Is that in a long channel MOSFET, during the channel pinch off, when the gate voltage is much below the threshold voltage, okay, gate voltage is much below the threshold voltage, we have to select the correct statements for each of the following. So then what we are going to do is that, if there we have to select the correct statements. Then during the channel pinch off, what happens is that almost no current flows. And why no current flows? Because we are talking about a long channel MOSFET. If you have a long channel MOSFET, if you have N plus regions here, if you have N-type gallium arsenide, I'm talking about just some N-type device. And this is gate, directly attached, Schottky barrier. This is gate. Then during the channel pinch off, because this whole is depleted, this whole region is depleted now, whole region is depleted, you will be having negligible current flowing through this. Okay, this is actually a for a long channel case. If you have a short channel device, then there will be this what you call as the depletion region will look like something like this. And you see that there will be some region here which will not be depleted. This is something called as delta region. Okay, and this delta particularly depends upon saturation voltage, and it depends upon maybe saturation current, it depends upon electronic charge, it depends upon doping, and it depends upon saturation velocity. Okay, basically, if you know that current is N area electronic charge times the let's say some velocity, then you can bring it down, you can play with it. Then you have the area factor, which is basically this factor coming, and you can write it as delta equals to I and D charge and saturation velocity. Okay, why saturation velocity? Because at this particular point, I told you that the electrons move down this hill at maximum velocity, which is determined by saturation velocity. Okay, saturation velocity concept I told in the previous session is just like terminal velocity of the rain droplets falling. Attain a constant velocity which is equivalent to saturation velocity. So if you have a velocity, you have an electric field, it saturates. It does not go beyond this particular thing. Okay, so this is E critical and this is V saturation. That's it. So this is the answer of this question. So there will be no almost no current flow because we are talking about long channel MOSFET. If this would have been a short channel MOSFET during the pinch off, then we would have we would have considered some current to flow, at least some current to flow. Okay, the current flow will not be completely gone. Okay, now what is beyond this? Now beyond saturation voltage. Now I talked about in the in this particular slide, we talked about the IV characteristics of this particular depletion mode MOSFET. If you have a if you have this particular structure, ID, this is ID, let's say in milliamps, you have VDS, then you have something like this, where this is the linear region, this is the saturation region. What about beyond saturation? It goes like this. Okay, this is the breakdown region. This is breakdown. So this is, and you see that these points which I have shown in the red, they are shifting. They are shifting how? If this is for VG equals to minus 2 volt, this is for VG equals to minus 1 volt, this is for VG equals to 0 volt. That means this particular thing are basically VD saturation. Let's say this is VD sat 3, VD sat 2, VD sat 1. These are the voltages at which these are the drain voltage at which the saturation of the current starts, and they are reducing as we go on increasing the gate voltage in a negative direction. Okay, so that is one trend. So this is linear region, this is linear region, so and this is saturation region, and this is breakdown region. You see the current increases abruptly in the breakdown region, it shoots up. And that is the third region we are going to say. What happens beyond VDS greater than VD sat? No, this is not right now the breakdown region. This is the second region we are going to talk about. VDS greater than VD sat. VDS greater than VD sat. So we are talking about this region, which is the saturation region now. We will be talking about what is going to happen in this region. Okay, so this is basically the region of our interest. And what happens in this region is now you have this that's the delta I was talking about, a small region which remains via which the current can flow at and the electrons can flow at a saturation velocity. Okay, so this is the region I talked about. This is the region I talked about. If you have the electrons here that can go down the hill with almost a velocity equal to saturation velocity. And now you have certain equations, and it doesn't matter how this equation comes up, you just have to solve something called as Poisson equation. You solve the Poisson equation and you get the voltage and the electric fields. And basically it is a two-dimensional Poisson equation because you have to solve it along this direction. Let's say this is x, this is y, then you have to solve v as a function of x, y. Now what is Poisson equation? You have del dot E, which is this particular thing you have to solve. Okay, this is a function of x and y. So you get these particular relations, and it's a very clear derivation. Maybe some of the books have mentioned it, but the concept here is that because now the electrons are flowing at a constant V sat, that means the current will no longer increase. Current will is going to saturate after this particular region. Okay, there will be saturation of the current. Saturation of the current. It doesn't mean the current will go to zero. Current won't go to zero abruptly after it, but after this particular point. Why? Because the electrons are still flowing. They are flowing at a constant rate. Okay, but they are flowing because the current depends upon charge. It depends upon number. The charge is constant. It depends upon mobility. It depends upon electric field. I should say the velocity. So if this is constant, then it will depend upon how many number of electrons are flowing. This is constant, then the constant current is going to flow. Okay. So this is the logic behind why this particular thing behaves constantly after it. So now there is a factor called as transconductance now. Transconductance. What is a transconductance? Look, if we add a page here, let's talk about the word transconductance. Because everything is mentioned in the word itself. This is trans, this is conductance. Conductance, it's the inverse of the resistance. That's as simple as that. What is trans? Trans means when you are measuring something between two different terminals. Okay, then you have to use this particular word called as trans. Okay, because this word is also in transistor. You might have heard about transistor. You might have heard about maybe transconductance or trans resistance, or maybe any other place. If you hear this particular word trans, that means two different things you are comparing, because this particular transconductance is the ratio, I shouldn't say ratio, it's the variation of the drain current with respect to the gate voltage. This is the transconductance. Now, what are two different things? This is drain current, this is gate voltage. And these are two different terminals if you see. This is N plus, this is N plus, this is gate. The drain current, if it is flowing in this direction, but the gate voltage is actually this here. It's a different terminal altogether. So you are measuring something between two different terminals. Okay, this is source, this is drain. Had it been a normal conductance, let's call it GN. I'm just not denoting it. Then it should have been the variation of drain current with respect to VDS. This is the normal conductance. But because it's trans conductance, that means trans means two different terminals. That means it's measuring the variation of the current here with respect to the gate voltage. So that's why if you draw a circuit element for this particular current, you show it something like this, and you write it maybe you write it GM times. You write it in terms of some. This is basically a what is happening? This is basically a voltage controlled current source. Okay, so you write it in terms of a current source showing like this. We will see how the circuit representation and small signal analysis looks like. Okay, so this is the concept of transconductance, and it's denoted by GM. So these particular relations, it doesn't matter how they come up. You just have to understand what those relations are, and there are certain aspects in this relation. This is the built-in voltage dependence. Built-in voltage is this particular voltage, which I showed you in the Schottky barrier. This is the built-in voltage. This is the Schottky barrier height. This is the something called as something called as Fermi potential. Fermi potential. Basically, it's EC minus EF. If you write it in terms of potential, then you have to divide it by Q. Okay. So this is the overall. This is the pinch off voltage which I talked about, at which the channel is totally pinched off, and this is gate to source voltage. Basically, this is this gate voltage. It's basically gate voltage, because if you are applying negative, you are applying here. You're grounding it, and you are grounding this to also. Not shorting. You are grounding it. This is positive. This is negative. So this is gate to source voltage. Okay. And why it's an important parameter? Why is it important parameter? Because it denotes that how much control over the drain current is of the gate voltage. If that means by increasing more GM, more control of gate terminal, and that is what you want. You want more control of the gate terminal in order to turn the transistor on and off. That is the fundamental of transistor. Otherwise, you could have just have two wires. You could have just a wire here, and you pass a current. Okay, and then you have to tap it on and off here in order to turn it on and off. That's not how what you do. That's not how you get amplification. You get amplification because of this particular thing. If you have now a third terminal here, if you somehow apply a voltage here so that you can turn this on and off, then you get a particular thing, different characteristics. You get on and off characteristics. You get switch. You get amplifications. You get so on and so forth, oscillations. Okay, so that is the fundamental thing about this transconductance. So high transconductance is better control of the gate, and it will be giving us high gain as well as high frequency. What is high gain and high frequency? If you have a MESFET like this MESFET, and MESFET may be denoted something like this, not this. This is MOSFET. This is MOSFET. MOSFET looks something like this. This is the NOx side. Okay, this is, let's say, NPN. Oh, what am I talking? NPN. This is source, this is channel, this is drain. And you apply some here, let's say, let me draw it opposite here because it's symmetric. So this is drain. You apply some VDD, constant voltage, and this is ground. This is gate voltage, where you apply your input signal, and this is the supply you give. because you have to have the energy source. Okay, this is the input voltage. And the output you measure across this particular thing, this is also grounded. So this is V output. All right. Okay. So in order to get the high gain, that means if this is, let's say the amplitude of the signal is A1 and you get V output as something like this, which is A2, then gain is basically A2 over A1 in simpler terms. And now how better this gain is, how higher this gain is, whether it's lower or higher, it depends upon this transconductance parameter. Okay. And it also controls the noise figure of this particular transistor. That's what we are going to see in the upcoming slides. Okay. So now, so this was about the transconductance. Now, what about there are certain approximations in this, something called as gradual channel approximation. Gradual channel approximation. This is also used in MOSFETs, by the way. It's also used in MOSFETs. It basically tells you to ignore the field along this direction and only consider the field along this direction, which is the controlling gate field. Controlling gate field. Okay, it's just that, and that's why it's only applicable to long channel devices. Why? Because the source and drain are separated by huge distance. So that's why if you have a Poisson equation, or whatever you call it, you have, let's say, dou E over dou X plus dou E over dou Y equals to, this is X, this is Y, equals to rho X comma Y divided by epsilon. Okay, now it will simplify your problem. You don't have to consider the variation of the field along this direction. You can just write dou E Y over dou Y equals to rho, maybe some XY divided by this. This is because this is partial derivative. Okay, you just have to solve this particular thing. Okay, so now how this is for the long channel case. Now what will happen in the short channel? In the short channel, you see that these denominator factors can become appreciable because this is dou E over some dimension, dou X. So if dou X this reduces, the overall factor is increase. Okay, it's just a mathematical thing. So this factor will become appreciable. You cannot ignore it. So that's why if you have a source and drain closer in a short channel device, then you have to consider the variation along X, variation along Y. I'm talking about the field variation, okay, electric field. So that is the gradual channel approximation. It says that the potential or the field varies gradually across the channel. So that is the fundamental thing. Okay, so now we have another question here. Another question is if you have to consider the MESFET, the built-in voltage is the same as pinch-off voltage. Okay, so first of all, what is the relation between the built-in voltage and the what you call as the pinch-off voltage? If you go back in the slides, maybe I have shown it here. Where is it? Let us see. Which question is it? Yeah, where did it go? Yeah, this one. So if you see the relation between the pinch-off voltage and the what you call as what is the question? Built-in voltage is same as pinch-off voltage. Okay. So it's saying that built-in voltage is basically same as pinch-off voltage. That means the threshold voltage is basically zero because the threshold voltage for these devices is built-in voltage minus the pinch-off voltage. Okay. So that means the threshold voltage is going to be zero. If threshold voltage is zero, that means you don't have to apply anything in order to, I should say, make the channel conduct. So the channel will start to conduct even at zero bias, zero voltage. So that is the concept of this particular question. Okay. Now another question we can move on. It's a little bit of numerical calculation, which we can actually solve. But I mean, maybe we can try. Yes, N-type gallium, N-type. It's an N-type device. First of all, that means it's ND doped. It requires such that the channel is turned off at gate voltage equals to zero. So that means the channel will turn off at VG equals to zero. Okay, VG equals to 0 volt, channel off. If the channel is off, that means ID will be equivalent to zero at this particular voltage. Okay, so it's a very good question. The Schottky barrier is the Schottky barrier, this particular thing is 0.8 volt. All right. So what are we given further? If we are given, assume that built-in voltage VBI, we have to assume is phi B minus 0.1 volt. Okay. The channel thickness. So there will be some channel thickness. So let's say this is depletion region, then there will be some channel thickness. Let's denote it as T. T channel 0.2 micrometers, and required channel doping. So there is some doping with, let's say, ND, which is A into 10 to the power 6. Oh no, it's not 6, it's B per centimeter cube. Okay, we might have to find the values of A and B. All right, so we need to find the values. Okay, so the values of A and B are, we have to take the permittivity and other things. Yeah, so I talked about the pitch of concept first of all. So here particularly, if you have VBI, or let's talk about in terms of the in terms of this particular thing. If you have this, is this particular thing given? We built in, yeah, V built in is given, which is given as phi B minus 0.1 volt. So basically this is 0.1 volt. Okay, so that means you can compute phi BI equals to phi B minus 0.1. Phi B is also given 0.8, which is the Schottky barrier, minus 0.1, that means 0.7 volt. So you have the built-in voltage is 0.1 volt. Now I think it's the question is over almost. Yeah, maybe we might have to find the V pinch off, because if you know V pinch off, then you can compute by using this equation, which is uh, this particular H is the 0.2 microns, which is given. Okay, so all other information is given except VP. VP you can find VP you can find by, because VTH equals to V built-in minus VP. Every other thing is given. You can compute VP, and you can bring ND equals to 2VP epsilon divided by QH square, which will be square root. No, it won't be square root. Yeah, 2H square. So this is the ND, which is the doping concentration. And when you solve this particular thing, you just have to do the some calculation. Maybe let me check the whether I have done the calculation correctly or not. Where is this? What is the answer we get after calculating? Hmm. Yes. So VT, this is 0, VBI minus VP. So VP is 0.7. Use that value here, and you get this particular thing to be equivalent to the 2 point some 5. I have actually got 2.6. I don't know why, into 10 to the power 17 per centimeter cube. This is the answer of this question. No, it's not 17, it's 16. 10 to the power 16 per centimeter cube. So after solving this, you can get it. Another way to solve this particular problem is you can use the W dip concept, which is the depletion width, which is basically twice epsilon over Q and D, some V of X minus VBI, uh, maybe some VD. This is the overall expression. This is the potential variation along this Vx, along this direction. Okay, then you can basically compute this potential variation by considering if this is, let's say, in saturation, or if this is at particular threshold, then you can write accordingly. Let's say if V equals to V saturation, then you can write, let's say, you can write, no, there is also VGS here, minus VGS, yes. And if the V is equivalent to VD sat, if the VD is equivalent to VD sat, let's say, then you can write basically VDS at VD sat. Basically, you can write it as VP minus VBI plus VGS. So you can use all other ways in order to solve this problem, but I think this is the particular easiest way to solve this particular problem. Otherwise, there are many equations in order to solve this particular problem, but this is the easiest way to solve it. But the important thing you have to use epsilon is epsilon naught times epsilon gas, gallium arsenide. Don't use the silicon. Don't do this mistake. This is 13. For silicon, I guess it's some lower value. And then epsilon naught is also given, it will be constant. That is about this question. And now moving on to the other question, which is about, I think it's similar, right? So this question tells us about we have to find the drain current. Or we have to find the drain current here. Okay, this is different. So what are the parameters given? This is a Schottky barrier. Schottky, is the Schottky barrier given? Yeah, Schottky barrier is given zero point 0.8 electron volt, and electron mobility is given 6 into 10 to the power 3 per centimeter square volt second. Channel width is given as, let's call it channel width W. I don't know how professor has denoted it, but let's call it W because it sounds good. And channel length, let's call it L. LCH is basically 1 micron. Channel doping, let's call it ND, which is 10 to the power 17 per centimeter cube. Effective density of states of conduction band is, let's call it effective density of state, and effective 4.7 into 10 to the power 17 per centimeter cube. So effective density of states is basically density of states at the bottom of the conduction band. If you have the bands, you have, how does the density of state look like with energy in a 3D case? If this is density of state as a function of energy, if this is conduction band, then density of state goes like this. If you consider all of those states, consider them all to be located at the minimum of the conduction band here. That is the effective density of state, which is N effective. That is just a hypothetical concept. In order to compute, you are ignoring all of those states, avoiding to considering them all at bottom of the conduction band. That is just the concept of the effective density of the states. And effective density of states is in per centimeter cube. And the drain current is basically we have to find, and VGS is given as minus 1.5 volt. Okay, so that is the overall scenario of this question. So this is the scenario of this question. So what do we need? We need a we need an equation for the drain current, and we need to see what it depends upon. So there is the equation. The equation is basically something like this, with mu n epsilon s q n d w dep and vgs minus vth square. This equation, but why it looks like this and what are the quantities we need to find from it? First of all, we will look out to the quantities we need in this particular case. So here this is VBI, which is the built-in voltage. Is it given? No, it's not given. Okay, we can find it because effective density of states is given. That means we can compute this EC minus EF. EC minus EF, it will be equivalent to KT by Q ln of N effective by ND. ND is given, which is 10 to the power 17. So you get EC minus EF. If you get this distance, then you can compute the built-in voltage. Basically, built-in voltage will be phi B minus EC minus EF. Okay, EC minus EF you have computed already. You use it here, and phi B is given. You will compute VBI. So that you have obtained the built-in voltage. Now, what can you get from the built-in voltage? You can even use, let's say, the threshold voltage for these particular devices is built-in voltage minus the pinch-off voltage. So you know this, you can compute this also. How you can compute pinch-off voltage? You can compute it by Q and D H square divided by twice epsilon. Everything is again given. Okay, so you compute threshold voltage. If you compute the threshold voltage, then I guess everything is done. You have mobility, you have epsilon, WL you have ND, you have W dip. W dip you have? No, you can compute W dip also. W dip can be computed by under root of twice epsilon by Q and D. You have V of X plus VBI minus VGS. Again, you have these particular quantities, you have VGS, you have the threshold voltage, then you can compute the drain to source current. And this particular equation, you don't need to worry. It just comes from the fact that you know about this particular thing. If you know about the NAEVD thing, you can write it as mobility times electric field. You can write it. You can just juggle with the things. Then you can write electric field as dou V over dou X. You can write it as in terms of the voltage. Then you can replace it with the length. And then you have the area, you have the number, you can replace it with ND. Then you have the mobility also. So these all come from these particular equations. You don't need to worry how these equations come up. They come from the basic electrostatic equations. And finally, when you solve this particular problem, we just put the numbers because this is the overall method of this particular thing. I guess you get the current to be equivalent to 16 milliamps. This is the overall current you will get from this particular system, from this particular thing. Yes, that is about it. You just have to put the numbers in this equation now and see whether they will work or not. And let me remove this. Let me keep it here. And what else? No, short channel. Now the short channel, what does the short channel thing say? Now, if you have a short channel device like this particular thing, that means that there is a the drain, the these particular are very closer to each other, and you have a very short channel present in between. That means the layer where the electrons are basically moving is very short, and those electrons are basically then moving at a saturation velocity towards the drain. And the critical information about the short channel is that the carriers travel at saturation velocity in the whole region below gate. It's because why? It's because let me show it graphically. It's because if you have a short channel and this is your gate, then if you draw the band diagram of it, if you can show it like this. There is a bending in the entire region because now this the bending created by the drain, it extends up to the in the whole channel. As a result of which, what happens is that because of huge electric field, the electrons move at Vsat throughout the channel. Okay, if you have a long channel, then it looks something like this. Okay, here the electrons didn't move with critical velocity, with the sorry saturation velocity. Here the electrons move. But now if you reduce it, you will see that it will become like this. As you go on reducing, it will become like this. It will become like this. As you go on reducing it, the band diagram will look like this, and you have more and more electrons moving with the that maximum saturation velocity. That's why you get a very faster device as you short this particular. As you lower this particular dimension, you get a faster and faster device. That means you get faster, or I should say the maximum frequency, how fast an electron can move from source region to the drain region. That is basically determines your frequency. Okay, something called as let's call it transit time. Transit time, tau t. Tau t will be given by maximum velocity of not velocity, distance, the channel length divided by the velocity of electrons, which will be saturation velocity. So this will be basically the transit time of electron. How long will it take for the electron to go from source to drain? And this transit time is the inverse of it, let's say ft, which will be equivalent to 1 over 2 pi tau t. This actually gives something called as frequency gain, or something called as the working frequency of this transistor. So there are two types of frequencies. This is one of the frequencies, the which basically determines which basically is with respect to the current. This is basically current gain frequency. Okay, so you have a plot of current versus you have a plot for gain. This is in decibels. This is frequency. Let's say in gigahertz. You have a plot like this, and this slope is 10 dB, or not 10, 20 dB per decade. What does it mean? It means that if this value here is let's say 20, and this value here is let's say minus, that's not considered, let's call it magnitude. This is 40, then this particular change, this is, if this is 100, then this is 100, this is 10, this is 100 gigahertz, and this particular change will be 10 times. Okay, that means 20 decibel per decade change. Per decade means 10 times. Okay, so as the gain will fall 20 dB, there will be 10 times change in the X direction, X axis. Okay, that's what 20 dB per decade means. So this is the gain profile of a typical, how the typical gain profile looks like. And if you if you extrapolate it experimentally, you see this particular point where you have a 0 dB, let's say. Okay, and the gain becomes basically equivalent to 1 because log 10 of 0 is not 0, log of what is happening to this pencil? I don't know. You see this point, this at which the gain basically becomes equivalent to 1. That means the current gain, which is basically denoted by ft, the current gain frequency, that basically becomes equivalent to 1, and the you can denote it in terms of the log scale. But where does it come from? That's what I was trying to tell you. It comes from because of the transit time of the device, and transit time denotes this frequency of motion of this particular electrons. So now you can replace tau t. You can write it as L channel divided by V sat. You can write it as V sat divided by 2 pi LCH. So you see that how important is this factor of the length of this channel. So now if you go on reducing the length of the channel, you can go on higher frequency devices. That means the time taken by between the source and the drain for the electron to go from source to drain will be lower. And you cannot play with this VSAT much because it's almost a constant maximum velocity. Okay, so that's why you have this factor where you can change this particular thing. We will see in the upcoming slides, there are other factors which can also change it. There's another frequency called as power gain frequency. Power gain frequency. Okay, so that is with respect to the power. That's the maximum frequency with respect to the power. Maximum frequency with respect to basically power. So that is where you can get a maximum power out. If this is in, let's say, power will mostly, let's say in decibel per milliwatt. This is the frequency. Then it is the it is the maximum I should say gain you can get out from it at some particular frequency. Okay, so that's why usually if you operate a particular device, you don't go on up to this point. Yeah, you can get a let's say a high frequency here, but you see the gain here is very low. That's why you try to operate it around here at this point, where you can at least have some maybe 100 gigahertz or 50 gigahertz frequency, and you have appreciable gain. So because there is always a gain bandwidth product is, or I should say gain times frequency, it's constant. Okay, it's just a trade-off. You go on playing with one, you are going to affect the other. Gain equals to, let's say, some constant divided by frequency. You go on increasing this, you will reduce the gain. Okay, so this is the one by x type of relation, which is the hyperbolic relation. Hyperbolic relation. So there are certain trade-offs, and there are a lot of trade-offs. It will be very difficult to cover those trade-offs in this particular lecture, and I hope the professor has almost covered entirely those particular trade-offs. There's a trade-off between what happens if you go on reducing the channel, capacitances comes in, quantum mechanical effects comes into picture, and so on and so forth. So it's there are I don't know infinite number of effects which can happen if there is a let's say if there is a if if this was for the long channel and then this is for the short channel where the electrons are moving with velocity v equals to v sat. So then there are a lot of other things which can happen in short channel. If you go on reducing the channel, these two source and drain regions will come so closer to each other that they will almost start to affect each other. Okay, so there will be electrostatic interaction between the electrons here, or even I should say, that particular effect is going to create certain capacitances, delays, and other things. So that's very undesirable. You cannot go it beyond certain value. So that's why this has now become a what should I call now because if you go beneath the certain channel dimensions, then you no longer are in the classical limit. What is the classical limit? Classical limit is when the electron's wavelength is much greater than the dimension. Which dimension? That is the channel length. So this is the classical limit where the electron wavelength is much greater than the channel dimension. And electron wavelength, this is the de Broglie wavelength from some basic quantum. And this is basically some h over the mv of the electron. And if the electron wavelength becomes comparable to the channel wavelength, then you have treated as a quantum mechanical particle, and it messes up with the system. People don't want to do some quantum mechanics in these devices because it's very difficult. It's tricky. It sounds cool, but it's very tricky to deal with quantum things in these devices. So that's why you don't want to deal with these quantum effects as such because they are very difficult to control, at least at the level where we are using the devices in your mobile phones, in all other things. So that creates a lot of issues, and so that's why now now there are certain other factors how we are coping up with this issue. Why we are not reducing now? Because now you see that you have seen from couple of years the frequency at which the transistor is operating, maybe 5 gigahertz, that has gone stuck because you cannot reduce the channel any longer. Maybe if you have a processor that has some processing frequency, that is maybe 4 to 5 gigahertz. It's max right now. You cannot find any new processor beyond this particular frequency. The reason is that because it has now saturated, you cannot go on reducing the channel length. Okay. And this is I'm talking about CMOS devices. Even in microwave devices where, let's say this is a microwave frequency, that means let's say you have a 50 gigahertz frequency or 60 gigahertz frequency. It's still a very huge frequency. That means for a electron to go from this to this side, let's say if we have a frequency of 50 gigahertz, then what is the time period? The time period of the signal is maybe 1 over 50 into 10 to the power minus 9. How much is this? 0.02 into 10 to the power minus 9. This is 2 into 10 to the power minus 11, or you can write 20 picoseconds. So this is the time period over which the electron has to respond. Okay, in which in where I should say, because you are applying this microwave as an input to the transistor, and then you want it to go as a to the output. You are using you are using it at a microwave frequency. Then the electron should respond at this time scale, and it becomes difficult for them to respond at this particular time scale. That's why there you will see that if you apply a if you apply a pulsed power, a microwave at a microwave frequency, and you apply a DC power, you apply a pulsed power, you apply a DC power, you will see two different effects in the signal propagating toward through in the transistor. Okay, because this is at huge frequency, this is a microwave frequency, so there is some time for the electrons to respond. That time is essential for the electrons to respond because electron has to at least, I should say, feel the voltage for certain some period of time. Only then it can respond. It's not that you give it any time scale. If you give it a very shorter time scale voltage and it's going to respond a similar way, then it's going to respond to the DC. DC is like you have the signal present at all the times, and you have a sufficient time for the electron to respond. But here, this particular width is very small. Okay, this particular width is of the order of 20 picoseconds. So you have to make the electrons to respond at that particular time. That is very tricky. Okay, so there are certain ways how we tackle it, and that is maybe in the next part we may be discussing about it. And there is some there's an effect called as current crowding effect. Current crowding effect that also comes into picture because of this. Okay, if you can just search for it if you are interested in it. Now we have a MESFET gate to channel distance as 20 nanometers. And what else is given? Select the gate lengths for which the output conductance is minimum. I think we have not covered it. Have we covered it? Let me check. Uh, okay, yes. So there is something called as gate to channel distance ratio. Okay, so basically the GM which I talked about, which is transconductance given as something like this. For these devices, MESFETs, if you do the calculation, this GM basically comes to be approximately equivalent to some factor Z. I guess this is the width or something. Epsilon S, Vs, divided by WDS. What is this WDS and what is this VDS? Basically, it is, let me just show you clearly. I have drawn it on a scale better. Where is it? Hold on. Because that is going to Clear the concept. Not here. Not here. Okay, these are certain dimensions of the device, but I don't know whether what what symbols professor has used. Would have been better if he would have used W and L for the channel, but I guess he has used different symbols. Where is it? Just give me a moment. I don't want there should be a mismatch. Hmm. So actually, the notation he has used is something like if you have this device and this is source, this is drain, and you have a depletion region like this, then this is something called as WDS. This is, let's call it B distance. Let's call this whole distance as A. Let's call this distance as WDD. And this is basically L. And this particular distance is H, which is A minus WDS. So this is basically the governing factor. L over H ratio, it determines the, what should I call, what was given in the question? Output conductance. Okay, so output conductance is controlled by this L over H ratio. So this is basically the gate to channel distance. Okay, so L divided by H is basically the channel distance. Okay, so it's technically something called an aspect ratio in the simpler sense. And for a typical device operation, for the output conductance to be minimum, and pardon me, this is not here the transconductance. This is the output conductance. So sorry for this. This is not. This is not. This is transconductance. Dou ID divided by dou VGS. This is transconductance. The output conductance is simply if you have ID versus VDS, the output characteristic. The output characteristic. If you have the output characteristic like this increases, then it saturates. This is what should happen. But what actually happens is that you have something like a slope. Okay, this happens because of something called as channel length modulation. Let's not talk about it. So basically, the drain voltage starts to control the channel, which should not happen. The gate should only control the channel. That is good. But if the drain also starts to control the channel, then it starts to modulate it. Okay, that's something called as channel length modulation. And the now the channel control now the channel comes under the control of the gate also, and you have something like output resistance, which is given by the slope of this. So the slope of this is basically slope of this is output resistance. It's basically 1 over output resistance. And then you can define output conductance as dou ID versus dou VDS. This is the output conductance. Okay. And it depends upon this ratio, L over H ratio. And for a typical case, it should be approximately 10. That means L should be approximately 10 times that of H. This particular dimension should be 10 times that of this particular dimension. Okay. Why? Because you don't want the drain, the channel length modulation or the output resistance to come into this picture. Okay. That means if you have that means if you have L equals to 10 times, let's say 20 nanometer, which is given, gate to channel distance is given 20 nanometers. That means it's 200 nanometers. This is at least, it should be greater or equal to actually here. So L should be greater or equal to 200 nanometers. So whatever is greater than 200 nanometer, this is not, this can be, this can be. So these two are the answer of this question. So L can be greater than 200 nanometer in this case. It can be 350 nanometers, it can be 500 nanometers for the output conductance to be minimum. Okay. And now we have the short channel MESFETs. Which of the following is correct for the short channel MESFETs? We have to give the correct answer. They are good for linearity. We have not discussed about linearity. And they are good for almost flat transconductance. What does this mean? Well, you want this to be constant. It means better gate control. control. Well, what does it mean mathematically? Transconductance is basically dou ID by dou VGS. If this is constant, what does it mean if we have a some derivative? Dou ID over dou VGS is constant. That means ID is varying. Let's call it some constant times dou VGS dou ID. That means ID is varying some as a linear function. Okay, what does it mean now? If you have, for example, a constant flat transconductance means a constant transconductance. Let's say, let me draw a figure like dou ID dou VGS. This is GS. This is transfer characteristics, not output characteristic. Just pay attention to this figure, and it looks like something like this because it starts from the negative voltage. Not dou. Why I'm showing dou? This is ID versus VGS. And this is -1, -2, not here. It increases like this. Yeah, that's what should happen. Okay, so now if you have to compute the transconductance, you differentiate it. And when you differentiate it, you get let's say this is the maximum slope, then you get something like this. So this is the GM plot, typically. You get a maximum transconductance at this particular point. So the better this particular portion, the maximum transconductance will be here. And what else is required? If you have a, you need to have a good linearity. Good linearity means it should be, what should I call linearity? We have not defined. Linearity is like if you have a signal coming in and you have a signal output from it. It should vary as a linear function of that particular input signal. It should not distort. Okay, so that is the linearity. If this is signal, let's say f of x function, if this is g of x, then you can write g of x as some maybe a times f of x plus maybe some c. So this can be this is like a linear function. They should be linearly proportional to each other. Not it should not be like g of x should be equivalent to maybe a f of x this square plus some c square. It will make it a non-linear function. Okay, because these quadratic functions are highly non-linear. But definitely because this is a transistor, then there will be some non-linearities in these devices. Actual devices have non-linearities. They have non-linearities as well as harmonics. Harmonics are certain other frequency components, and they come because of many factors. If you have a microwave signal coming in input, let's say this is a 60 gigahertz, then if you give it input to a transistor, let's say MESFET or any other FET, then in the output, if you check this Fourier transform of this, it will have a peak at 60 gigahertz. Okay, let's say these components are negligible, but at the output, when you see the Fourier transform, you get something like you get a 60 gigahertz, then you get another peak here, then you get another peak here, and so on and so forth. So this will be maybe 60 gigahertz, this will be maybe 120 gigahertz, this will be 180 gigahertz. So this is the first harmonic, this is the second harmonic, so on and so forth. So this is something called as harmonics. And these arise because naturally you cannot have a system without these harmonics because in the Fourier series, when you write the Fourier series, you see that there are those harmonic components present there. And you cannot just feed a single signal and expect to get output signal because there are certain what are basically controlling these things. These are controlled by capacitances, inductances, okay, and they are frequency dependent components. Resistance is not, at least. Okay, so that's why these particular frequency components, different frequency components come into picture. And the deeper reason is something different. You might have studied about something called as classes of amplifiers. So you might have to study then class 1, class 2 amplifier in order to understand those harmonics, second harmonic, and even certain classes of amplifiers uses these higher harmonics. If I correctly know, I'm not sure about it, but maybe certain in certain ways they can be used. Okay, So this is the Fourier transform. Let's call it FFT, Fourier transform. So now the breakdown. Okay, so breakdown is basically what is breakdown? Breakdown is this particular region. If you have ID, you have VDS, it linearly increases, saturates, then it goes high. If the VDS becomes greater than V breakdown, not only VDS, even if VGS increases to a value something called as critical voltage or critical electric field, it can cause severe breakdown. And there are two types of breakdowns that can happen. One can happen if you have a device. This is like this is gate. One can happen in this direction. This is breakdown of the Schottky barrier. If you zoom this here, zoom this part here, you have a Schottky barrier. This is Fermi level. This is the barrier like his. Okay. If this breaks down, then it will break down because electrons will start to flow in this direction into the channel, which should not happen. Either it will tunnel or there will be thermionic emission. This is tunnel. Okay. And another breakdown can be at this particular point. If there is huge drain voltage, then there will be impact ionization because the banding is like this, electrons are going down the hill, then there will be impact ionization and other things, impact ionization and uh, other factors like impact ionization, avalanche breakdown. That's basically impact ionization. Okay. So these two breakdowns can create a lot of problems in these particular devices. Particularly, they won't allow you to control they will swing the transconductance. They won't allow you to remain in the saturation region. They will give rise to huge currents in the devices, and all of the control will be lost. Okay, so that is what we have written here: thermionic emission, field emission, reverse biased gate. If you reverse bias it, Schottky junction, this is gate. Okay, and this is positively biased, then there is a tunneling probability, then electron can go over the barrier. Okay, and there are a lot of other factors. There is something called as Fowler Nordheim tunneling, and there is something called as direct tunneling. Okay, basically tunnel. How does the tunneling happen? Let me just show you on this page. If you have different scenarios. If you have a triangular barrier just like this, then electron can tunnel through this. But if you have like this, and you have a let's say this is another energy band, which is like an oxide. Let's say this is an oxide, maybe some silicon dioxide. This is basically the conduction band of silicon dioxide. Then if an electron tunnels to this site, to the conduction band of oxide, then rolls down the hill and goes to the other side. Let's say you have some conduction band of some other substrate here, comes down here. This tunneling is basically given a different name. I don't know the name doesn't matter. And this tunneling is basically a different tunneling. It's, I think, a direct tunneling. And I guess something like Fowler-Nordheim tunneling looks like this. The name I don't know, but these are the concepts how the tunneling can take place. Either it can go to a state or it can directly go to the other part of this barrier. Let's say you have the barrier like this. If it goes directly, then it goes directly down the hill. If it comes here and occupies the states, then goes down the hill, then it's a different type of tunneling. So okay, so these all can create breakdown because you don't want the electrons to come from the gate to here at the channel region. That is going to create damage to this device by increasing the current without your control. Okay, now doping profile for flat GM. Okay, let's skip this part if I can see whether there is enough time, or I think professor has covered this particular part because I've taken this from its slide. Yeah, from now let's talk about let's talk about this. I don't want to skip it. This is like doping profile is like doping of this. How do you dope it? Let's say if you have n-type gallium arsenide here, and if you have n plus regions here, then whether you dope this region uniformly, whether you dope it, let's say, uh, let me draw it exponentially, or whether you dope it as a delta function. Okay, it is going to have an impact on the GM characteristics because that is particularly dependent on this doping concentration and how does it vary throughout the channel. So if you have a uniform doping, then you have uniformly present ND throughout. If you have exponentially increasing doping, then you have the doping something like this. Okay, where if this is 0 to A, it reaches maximum at this particular point. If you have a delta doping, then delta doping is something like present here as a delta functions. So that's what basically is shown. This is a delta function. Delta function, that means if D tends to A, it will be a delta function of let's say X. Okay. And this you see if D by A is 1, that means D equals to A, you have this particular flat line. That's what you want basically. You have this flat line, this red one here. Okay, that's the ideal scenario what you want. That's why most of the time these exponential and delta dopings are used in order to improve the transconductance profile of these. Now, if you talk about gallium arsenide MESFET structures, okay, these are related to fabrication. I guess professor has covered it in detail. So these are related to fabs, how you fabricate these devices, and uh, you take initially a substrate, then you create deposit another layer, and then you do certain steps which are basically shown in this particular picture. Okay, so initially starting with the certain wafer, gallium arsenide wafer, then you implant certain layers, then you again deposit certain I should say contacts. And there are multiple number of steps. It's just like the deposit, or I should say fabrication is just like cooking. In cooking, you have the recipe, and you are given the recipe. You are given. Okay, then you have to optimize it, and the finally you have to see how better a dish you can make. And it depends upon how well you have cooked, how better cook you are, how well a device you can get at the end. It's just a matter of how good a cook you are. It's just like a recipe. Okay. So that is the fundamental thing of the fabrication, and it's present everywhere. There is no what should I say? It's just like things you have to remember. You don't have much to think about in these particular fabrication things. I should say because these are established things. Okay. You just have to think in terms of a structure, how well you can make a structure over this particular thing, how well it can be supported by the base, how well if you have to make a gate like this, if you have to make, let's say these are sources, these are drains, if you can make a gate like this, then whether this gate can be supported by this particular structure or whether it will collapse. Then if you have another metallic layer here, another metallic layer here, you want these to be separated, these gaps to be large enough in order to avoid any of the parasitic capacitances here or even the short circuits here. Okay, so these are just the how you make the devices. Okay, that's a different thing. How it comes into the picture of a circuit, that is what mostly we have to deal with. So this is basically dealt in the fabrication. So it's a very tedious task, to be honest, because you have to, in order to do one, I should say layer by layer, in order to do it, you have to be sure that every time you are depositing something, it's not going to disturb any other thing. Just like if you are removing this particular thing by maybe sputtering or any other thing, lift off using certain chemicals, you have to ensure that it's not removing these particular things also. And most of the time, it happens that it removed something that you don't want to remove, and then you have to go back to the step first. You have to start making it from the step one, then move to the step again. Okay, so this is a very tedious task, and it's a different thing than I should say device circuits, physics, device physics, and other things. You just have to optimize your dish and how better you can make a dish. Okay, so now certain questions about these particular fabrications is given. A heavily doped N-type layer is required under the ohmic contact, but not under the gate. The most feasible and easy process is that growing heavily doped n-type layer and etching this layer for the gate and SS region. Okay, so it's saying that heavily doped n-type layer is required under ohmic contacts. So if you have this, if you have n plus, these are basically ohmic contacts. These are ohmic. These are not Schottky, not Schottky, because you want the contact resistance to be as minimum as possible. Contact resistance to be minimum as possible. Okay, so it's saying that heavily doped n-type is required under ohmic contacts. Okay, yeah, heavily doped n-type is required under ohmic contacts. Okay, but not under the gate contact, but not under this contact. Why? What is the most feasible and easy process? I mean, it's basically a fab question. What will be the most easy way to do it? Well, what is the first option? First option is growing heavily doped n-type and etching this layer for the gate and SS region. Selectively growing heavily doped N layer for the ohmic contact, selectively growing low dope, selectively growing low dope. Growing, okay, so let's discuss part one, growing heavily doped N layer and etching this layer for the gate and SS region. So if you see this picture, whether it's shown here, hmm, would have been better if it would have some visualization. Okay, so the basically the answer is this, what this is basically saying and why this is important. So there are basically considerations that if you dope it early, heavily, and then you etch certain layer for the gate and the SS region. SS region looks something like this. Okay, in order for the gate to be deposited as a metal, because this is a metal and this is deposited by, let's say, something called a sputtering. Sputtering is like you have a metal target, let's say nickel, and you kind of apply some external potential in order for the nickel atoms to get deposited over the substrate in this region. But you have to cover every other thing in this. You have to cover this thing, you have to cover this thing as this, and then this particular thing is deposited here. Okay, so these are different fabrication steps, and I don't want to go into the discuss in details because these are not related to this particularly how you want to fabricate these. There are a number of references available how do you fabricate effectively in this particular structure.
Sir,
Okay, so now, if you see the
hello,
question number 8, it says in gas MOSFET, gate priority
hello.
self-aligned process refractory metals are used. Okay, yes, this concept I will discuss because this is very important and mostly it may be asked in certain things. So, what is the refractory metals? Basically, when you have a structure like this, N plus, you have certain contact here, you have a gate contact here. So when you make this gate contact, it's not actually a single metal. What you consider if you zoom it, this is a metal, this is metal, and this is then actually it's made up of different layers of the metal. This is
Hello,
metal 1, this is metal 2,
hello,
and this is metal 3. Okay, this is like this. So these are made up of stacks of materials, stacks of metals. Okay. We have. Do you have any question? I cannot
hello,
hear you.
hello.
Just wait a minute. Wait a minute. Wait a minute.
Shajan
Any
bhai,
audio
am I
issue in
audible?
my microphone? Stereo. Hello?
Hello, Shajan
Yeah,
bhaiya.
yeah, yeah, yeah. You can say now.
Am I audible now?
Yeah, yeah. Now you're audible. It was an issue with the
Okay.
microphone.
Bhaiya, you're saying about contact resistance. Like,
Hmm.
if we give very hard deposition, will is there any way to remove the contact resistance?
If you give,
Very hard contact, will it eliminate contact resistance?
no, you cannot totally eliminate the resistance, to be honest. Look, resistance will always be there. Because why? Because you are at the end of the day, this is a contact between two different materials. This is a metal, this is a semiconductor. So at this junction, there will always be some resistance to the electrons, scattering, other things, so on and so forth. Okay, even I'm telling you, if you have a metal and if you deposit it over the metal, still the resistance will always be there. You cannot reduce it. Resistance is intrinsically there. Okay, now why is it even there? And why does it happen so the resistance is there? It comes because from the thermodynamics. Now you have to go to the thermodynamics and you have to see something called as Gibbs free energy and the temperature dependence and other things. Okay, entropy and other things. But I'm telling you that this resistance cannot be reduced to zero. That's the fundamental thing. Whether it's contact, whether it's in the device, whether it's anywhere, it cannot be reduced to zero. What you are saying is that if you have a gate, if you deposit it over the semiconductor substrate, if you annihilate something called as annealing, that is a hot temperature, what you were saying. Hot temperature, it's heated so that it can at least diffuse to a certain extent toward into the semiconductor so that it will make a good contact. But it won't be a zero resistance contact. Never. Because there are so many imperfections here, dangling bonds, surface states, defect states, traps, so much so that they are going to trap electrons. They are going to what should I say, scatter electrons. Let's say if you have a metal like this, and if you have a semiconductor like this, and if you have semiconductors Fermi level like this, let's say these are all flat. This is metal's Fermi level. Then you know that you have surface or trap states here. So what will happen even if there is no barrier here? Like if the barrier looks something like this, let's say electron will go from here to here. Then now you are saying that you want to reduce the contact resistance, but what will happen? The electron will be trapped by these states. So once it's trapped, it created resistance because let's say 100 electrons came from here, 90 went here, but 10 went into the traps. So that is resistance. So that is this resistance. You got the point.
Yes, I got it.
So and this is just one reason. There are so many reasons why this contact resistance comes into picture. And why does the resistance even come into picture? That is basically from the thermodynamics. Now, I don't want to go into that detail. That is a matter of almost 2 hour discussion. But the resistance will always be there. Okay. So now I was talking about
Okay.
metal stacking. Stacking is done in order for, let's say you have, what should I say? It is basically for the ease of fabrication. In order for to survive, for some metals can survive, some metals cannot survive. What do I mean by survive? Is that if you have a if you have this one layer, another metal, if you have, let's say, gold, maybe you have some titanium, let's say you have some nickel or any other thing. Mostly Thai gold is used, nickel titanium is used, nickel gold is used. These are the refractory materials which are used because this gold, it is inert. It does not react to the other things, other chemicals as such. So any chemical which is in which it is dipped, it won't react to it because you have to dip your transistor, whatever you are making, you have to dip it in certain chemicals while doing, let's say, etching process to remove certain layers. And there is something called as wet etching, in which you literally dip it in some chemical in order to remove it, in order to remove the metallic layer or some other layer. Or there are many fabrication steps wherein you have to use the chemicals. But if you don't want that to affect the metallic layer, then you can use the gold over it. This titanium can be used as a barrier, let's say, so that the electrons cannot flow from here to here, or it cannot affect the any of the electrons in the nickel. And this will be the actual metal then, which will be basically providing the electrons into the not electrons, providing the field effect towards the channel. And then if you have a MOSFET, you can have oxide. If you don't have a oxide, then it will be directly connected and it will be making a Schottky barrier. And the selection of this metal basically depends upon basically the work functions of the metal. Because you want to make a Schottky barrier, you want to make a barrier like this. Okay, you want this work function. This is an equilibrium. This is an equilibrium. But you want the work function of the metal. This is phi metal. This is phi semiconductor. Okay, so if this is Before joining, you have Fermi level of metal, and this is, let's say, vacuum level. This is vacuum level. Let me draw it here. You will be get confused. If this is vacuum level, this is Fermi level of metal, and this is Fermi level of semiconductor. Let's say this is N-type. Then before joining, what is going to happen after you join? The electrons from higher Fermi level will go towards the lower Fermi level. As a result, it will increase the potential here. That's why this band bending comes up, and it will become here as this. Now electron can no longer go in, and in equilibrium you have a flat Fermi level. Okay, so that means this Fermi, this work function difference, phi m should be greater, phi m minus phi s, which is the work function of metal minus semiconductor, is an important parameter in determining whether you make a Schottky contact or whether you make a ohmic contact. So that is why it will be important in deciding this metal. So that's why these refractive materials are used. And what is the answer of this question, which basically is question number 8? It says that it says that in gas MESFET gate priority self-aligned process refractive metals. So this is called something called as refractive metals are used because of they are used to because withstand high temperature of ohmic anneal. High temperature means that's what I said. Certain chemicals they have to bear certain certain high temperature steps, which is basically used for annealing. That's what I was telling you. If you want to anneal the metal and you want to make a diffuser more towards the semiconductor, then if you want the it to withstand that higher particular temperature of the order of, maybe I don't remember the exact value, 1000 Kelvin or maybe 500 Kelvin, then it can withstand that particular temperature better. Otherwise, what will happen if you heat it a lot more? Then it's going to kind of, I should say, melt or rather diffuse a lot into it and totally destroy I should say, the semiconductor, and the contact will be poor. So that is the important point here. But it will be also important if you want to protect it from certain chemicals. That's also going to be important. Okay, let me have some water first. We're almost about to end. I guess how many slides are left? Okay, three more slides. So we are almost about to. So now these are certain fabrication steps, and these things keep on changing. They are not constant things because people try different things to improve the efficiency of a device. Somebody came up and designed a gate like this, and they saw an improvement in the device. This is the other dimension. But what when they make it, they saw that there's a capacitance here, there's a capacitance here, because this region now is closer to the drain, this region is closer to the source. Okay, so this is something called as mushroom type device, mushroom gate. This is called as head of the mushroom. This is called as the, I think, the foot of the mushroom. Okay,
Maya, what is
so
that noise means?
sorry.
What is that noise? Good for noise and F max. Reduce.
Okay, reduces gate resistance and other things. So I'll tell you what it is. Let me, yes, this is where it is. I have actually explained it in a better thing. Yeah, yes, I'll tell you in this way. So if you have let's say if you don't have a mushroom gate, if you have a simple gate stack present, which is just like a rectangular bar, then you have basically the gate resistance in this direction. Okay, this is the resistance provided by the gate. This is, let's say, the thickness of the stack. This is, let's say, the gate length, and this is, let's say, the gate width. Okay, and then you know that you can write the gate resistance from simple basic 10 plus 2 as rho W over T times Lg, which is basically rho W over area, cross-sectional area, basically cross-sectional area. So you can write the gate resistance as exactly like this. So if you, let's say, lower the gate length, it will increase the, what should I do? What if you lower the Lg, it will RG is going to increase. And if you, let's say, increase the T, the RG is going to reduce. So you want to reduce it. So you want to play with these particular structural parameters. And LG you cannot much change because that is the overall this particular area, because the more of this area is over the channel region, more will be the control over the channel. So you don't want to play with this particular thing. Okay, because this is a field effect. So the larger the L, the better will be the field control over the channel. Okay. So now what you want to play with? You want to play with maybe thickness, you want to play with maybe W. Okay, so that's why people play different games with it. And if you can control somehow, let's say W here, and let's say maybe you have L here, you have a larger L here, and as a result, you will be having different resistances in this particular metallic stack. Okay, now I told you that this is particularly important. This is going to have certain capacitances. Capacitances. Okay, capacitance, why? Because there'll be some coupling here. Coupling capacitances comes into picture anytime if you have if you have some charges separated by certain distances. That's it. It's not a real capacitor, a parallel plate or something. Whenever you have charges separated by certain distances, certain positive charges, negative charges, you will have capacitances. And what these capacitances they produce delay because they are charge storing elements. What does charge storing element do? It will produce delay. Let's say you have a channel and you have let's say you have a channel. This is channel, and channel you have some resistance and you have some capacitance also. When you model it in a circuit, you have some capacitance there also. Why is that capacitance there? Because certainly there will be, let's say, some regions where the charge will momentarily stay. It should not be there, but it can be, because let's say if you have a resistance, you have a capacitance. If the
So
electrons
even
moving
when there is no
in,
physical gap, there can be some capacitance by some insulating layer or something like that.
say again.
Like even though there is no physical gap, there will be
Uh,
some insulating layer, so this capacitance will come like.
Yeah, exactly. This is some dielectric. Whenever some dielectric, or let's say some kind of a separation between the charges, it is not a physical gap. It is not a dielectric event. It is some separation of the charges. If you have electrons here, if you have holes here, it is separated by some distance in space, which is x. You have a capacitance here. This is a capacitance. And what will this capacitance do? Because now the capacitance is basically a kind of a charge storage type element. If it momentarily stores charge for a brief moment of time, that storage will create delay. And that is a very bad thing in a device. You don't want, sometimes you want those delays. But if it is not a delay that you want, if it is what should I say? What's the correct word? The correct word is that if it is not the required delay. If it's the delay that you don't want in a circuit, then it can be a bad thing because it is going to cause a lot of stuff. Let's say you have a let's say you have a clock frequency at maybe maybe 1 gigahertz, and if this delay, let's say, created by the capacitance goes on increasing, let's say some delay of even 1 nanosecond is created, then it can create a huge problem in the device. That means it will at least slow down the device by 1 nanosecond. 1 nanosecond is small, but think about there are 1 billion transistors, not 1 billion. Right now, there are 50 billion. Okay, I'm talking about in a processor. If there are 50 billion transistors, then you can accordingly see how much delay they will create. At a single transistor level, it sounds like you have 1 nanosecond delay. What is it going to do? Definitely it won't do anything. But when you sum up all billion devices, then it's going to create a catastrophic delay. Okay, because all of those transistors will give one delay, 1 nanosecond, and it will cause a huge delay in the information flow, and it basically slows down the devices. Okay, and that is very worrisome. Now, what is going to be the next for a lower gate resistance rectangular? And yeah, that's what basically this F max is. So whenever you have a delay, time delay. It's associated with the how much maximum frequency you can play with it. How much how much fast an electron can move from this region to this region. It basically depends upon if you have any delay or any other capacitive element present in the circuit. Okay, and that is why this particular transistor, these particular high power, high frequency devices, the better way to model them is something called as transmission line approach. Transmission line approach basically takes into account resistances, capacitances, inductances, then resistances, capacitances, inductances, so on and so forth. Why does the inductance come into picture? That's a different story. But the resistance, capacitance, let's say, then you can basically solve maybe using Laplace in these loops. Maybe Laplace transform you can use for R, C, L. Then you can basically get a equation which will give you
But
in
yeah,
terms
a
of the frequency.
capacitance and resistance can be like understood. How inductance will arise there? Like,
That is the question I actually once asked one of the professors. And there are different reasons why inductances can happen. What is basically an inductance? Let me ask you.
like if the
This
loop
is
is there,
inductance.
like, yeah.
What is inductance?
If there is any current carrying loop, then
Yeah,
it will induce magnetic field. So that
exactly.
will be
So what happens basically? This is just a one device I'm showing. It's a gate and blah blah. So actually, what I will draw it in the next slide. It is the slide. So actually, how it is made, because this is just a one device. Okay, so there are multiple devices that are made, and they are made like something called as finger-like structure, multi-finger structures. I'll tell you what it is. They are made like this. Okay, these are like certain controlling gates and other things. These are gates. Or rather, the best way to be shown is that you have a single gate, you have a source, you have a drain, you have a source, you have a drain, you have a gate. One element goes from here, here, here. Okay, so you have these multiple interdigitated circuits. And whenever this becomes huge, this becomes larger up to let's say a certain length, then these particular particular metallic plates start to interact with each other. Okay, this is just like a, what should I say? Uh, because anytime you have a, let's say, a current flowing in the circuit, if you have a current flowing in the circuit, not even a circuit, even a metal, if you have a current flowing in the circuit, then it's going to it's basically going to generate a field around it. Okay, that you know from the basic Maxwell equation. And when you have such large number of elements present together, that is going to create an like a effect similar to that of inductance. And what is that inductance effect? Just like a capacitance, the current through the capacitance is C dV by dt. The we have the voltage across the inductance is L di by dt. Okay, so what is going to happen is that you will have certain type of effect where they will be where you have to take the inductances into account. And one important thing to note here is that, let me tell you, if you have a if you have a transmission line, the transmission line is like a line which is like a cable you have going
power
over the
line.
head. Yeah, exactly. So why do you model it as a resistor, capacitor, inductor? It's just like a wire. It's just a metal wire, because you have a current flowing through it. And whenever you have a let's say a time varying current flowing through it, it is going to produce the field around it, because these are all working at microwaves. And what is microwave? It's a time varying field, right? You got the point.
Yeah.
So these are all time varying things. If it would have been a static DC thing, then it's constant with time. Then you don't have to consider most of these things. That's why when you pass the AC current through the metallic wire, which is the transmission line, which supplies current basically to our homes, so on and so forth. That's why you have to consider these particular things, and in particularly AC circuits, because they come into picture in these time varying circuits. And that was basically one of the rivalry between between, I guess, Nikola Tesla and what is called as uh, what was the other one?
Edison.
Yeah, Edison. So he wanted to the Edison wanted to do the DC thing. The other one wanted to do the AC thing. Finally, we know that the AC thing won because of certain other reasons. But Edison gave certain, I should say, reasons like this. So it's a different story, but this is the particular thing, because once you are working at a time varying fields, then the time varying thing is going to create this time varying currents, time varying voltages, and these are basically the elements which will be created. Just like if you have if you have a transmission lines, you have another transmission line, another transmission line. And even what happens if they are separated in the air, they create a certain capacitance in the air. Okay, that is the way you model it, as this, like maybe some inductor, then you have some resistance here, capacitance here, another inductor, and you model it like a network. Then you have to do some analysis using Laplace transform and obtain the frequencies, poles, and zeros. That is going to give you certain other things. That's a different question. But my point is that this is the actual circuit diagram of a small signal analysis model. Small signal means if you have a very small fluctuating signal, which is slightly few greater than maybe some milli electron volts. Okay, that is what is termed as a small signal. Okay, you have a DC, then over the DC, there you are writing a small signal which is fluctuating AC. So that's why you write the overall, let's say, some current as some DC part plus some maybe AC part. So that will be the overall signal. It will be current or it will be voltage. Okay. So this is the overall schematic. So this is for the small signal. And one important thing to note here, when does this transmission line approach becomes important? It becomes important when when particularly the what should I say? Just like the electron's wave nature becomes important when the wavelength of electron becomes approximately equivalent to the dimensions. Or in other words, the dimensions of the system becomes equal to the electron wavelength. Similarly, when the microwave, the frequency you are dealing with, they become comparable, comparable to sizes of resistance, capacitance, inductance, so on and so forth. That time you have to use the transmission line method approach. Now you will say that you just mentioned that there is not a physical capacitor. So where is the size coming from? So the size is coming from, because if there is a capacitor, that means there is some electron, there is some holes, and there is some separation. If this separation becomes of the order of the wavelength of frequency of the incoming microwave. So if you have a microwave at 50 gigahertz, if you have a microwave with frequency 50 gigahertz, then what is its wavelength? It will be 3 into 10 to the power 8 divided by 50 into 10 to the power 9. Oops, it will be minus 9. So it will be 3 over 50 into 10 to the power minus 1. So how much is it? 53, 0.0056, 0.06 into 10 to the power minus 1. So it will be 6 millimeter. So you see, it is how the wavelength of this particular microwave becomes. And even if you go on increasing the frequency, you will reduce the you will go on reducing the wavelength. And when it approaches to the dimensions of those charge separations, how much the charges are separated, it will create a different effect. Because whenever the frequency or the wavelength, whenever the wavelength of an electromagnetic wave or any wave matches the size of an object, there are effects which occur. Like if an electromagnetic wave, let's say this is an electromagnetic wave, even a light wave, if it approaches to a frequency or the wavelength where it match the size of an object, let's say object of size A, then you know that there can be another effect like diffraction and other things, so on and so forth. That is a similar thing what happens here because you have microwave frequencies and there are, oh my God, there are thousands of possibilities that are going to happen. But they are mostly applicable then when you deal with the, what should I call, very high frequency waves. And that is the particular thing. Let me talk about now this thing. So this circuit is quite simple, looks complicated, but this is quite simple, where this is basically the direction of the current ID, which is GM times VG, because GM is ID over VG, the transconductance I told you. And this circuit element, you know, it is a GM times VG. That means it's a voltage controlled current source. This is a current source, but it's a voltage controlled current source. If it would have been like this, then this was, if it would have been something like maybe there's something called as current controlled current source, voltage controlled current source, current controlled current sources, voltage controlled voltage sources. So these are different, something called as dependent sources. This is like, I guess, semester one or two in BTech electronics you might have studied. Okay, and there are certain things which come into picture. This comes because of the gate resistance, which we talked about. This comes again because of the drain resistance, because of contacts, the source resistance, again because of contacts. This is the channel resistance. This is always going to be happen because electrons scatter, and there will be some resistance to the electron motion, and as a result, there will be resistance in the channel. This is drain to source capacitances. Again, there will be delays because of those capacitances, certain charge storing elements. And all of the things are, I guess, they can be quite explained in a similar way. And what is other thing? This parasitic can arise because of, let's say, if you have a mushroom type of gate structure. But anyways, they can also occur because there is this spacing is basically very small. We're talking about a nanoscale device. Okay, even a micro scale device will have, I should say, very small distances. So now what else is there? Are we done? How many questions are there? One, two, three. Oh my God, how many? This shoot 35. Okay, okay. Let me start with the what is important right now. Okay, I talked about the. This is basically the two frequencies which are important. The one is current. I talked about it. I think I talked about it. Yes, current gain frequency and power gain frequency. Power gain frequency. I talked about it in the previous slide, and there are some certain relations. Basically, this related to the transit time of the electron, how fast an electron can go from source to drain, and other things. And this particular relation is important between the between the power gain frequency and the current gain frequency. This is current gain frequency, and and obviously you see that F max is going to be less, I should say, less than Ft, because there is a factor of this particular thing. That means it depends upon the gate resistance, it depends upon gate to drain capacitances. Okay, so now that will might be one of the questions. In a MESFET, the intrinsic transconductance is this. No, this is about the intrinsic transconductance. Okay, now what happens is that if you have a device and if here's the gate, I talked about the transconductance. Okay, which is this particular thing. Let me just whether this is, yeah, I talked about this transconductance, but basically this is not the transconductance exactly we measure externally from the circuits. This is something called as intrinsic transconductance. Intrinsic means it is present in this particular section. When you bring these particular things into picture, then you have to consider something called as extrinsic transconductance. Extrinsic transconductance, because the transconductance will, this is just like an ideal scenario that only the drain current variation with respect to the gate voltage, that is intrinsic transconductance. But you know that other things like the maybe the some resistances, source resistances, and capacitances can come into picture. Drain resistances, they can basically deviate from this resistance. So that's why you have a extrinsic transconductance. Let's call it GM dash. It's basically intrinsic transconductance divided by 1 plus source to drain resistance times the intrinsic transconductance. And you have to compute the major transconductance, which is the extrinsic transconductance you measured. So it can be simply given as 0.2 divided by 1 plus the overall contact resistance is zero point 0.2 and channel access resistance, the gate resistance is zero point 0.2 also. So RS basically takes into account both the contact resistance as well as the gate resistance. Okay, so it is just like, well, how will I show you? It's just like contact resistance, the channel resistance, and the gate resistance. Whether it is shown in the previous figure, channel resistance, and they have not shown the gate resistance. Basically, it is the source resistance. Yeah, it will be in series, then it will be zero point 0.2 plus zero point 0.2, that will be 0.4 ohm millimeter. We've talked about this concept in the first session itself, why it is ohm millimeter. And yeah, it will be then 0.4 then into zero point 0.2 which is given, then you get approximately the answer as 0.2 divided by 1 plus 0.08 which is 0.2 divided by 1.08 which is 0.185 Siemens per millimeter. So the answer of this question is 0.185. Let me still check whether I did it correctly. Mm, 0.185. That is the answer of this question. Siemens per millimeter. Now, the FET is unity current gain frequency. This is FT, which is the current gain frequency. This is the F max, which is the power gain frequency. So I told you the relation between F max and FT is under root of FT divided by, what was the relation? Uh, this one, 8 pi RG CGD, 8 pi RG CGD. So definitely F max is less than Ft, which is basically shown also here. This is Ft, this is F max, it's very smaller. So it's showing to select the correct statements. The correct statement, what it will be? It's a FET with deeply scaled gate length with extremely high gate resistance. Oh, the FET is used. Yeah, one of the things can be it's a FET with deeply scaled gate length with extremely high gate resistance. If this factor goes on high, this factor will reduce drastically. That is what you see. The Ft is basically much greater than F max here. That one way can occur that gate resistance is huge. Okay, another factor can happen if CGD is huge, but this is not given in the question. So this particular factor seems to be looking good. And FET is useful in Q band application. I don't know whether the frequency falls in the Q band. It's much greater frequency than that. Extremely low gate resistance but high channel resistance. No, the gate resistance is huge because of this particular. Okay, now question 13. Take the statements in context of microwave power FETs. Okay, what is it saying? The gate range spacing determines breakdown, but not the operating frequency. The gate range determines breakdown and op yes, that's what I was telling you. That if this is drain side, the electrons are going down, then how much you can play with this region, which is gate to drain region. That will basically determine your breakdown. That's what I told in the first initial slides. Okay, because you will see that there will be impact ionization and other things that will break down the device. So you can play with these lengths, and it's also going to determine your operating frequency of the device. Okay, because operating frequency at the end also depends upon, let's say, 1 over 2 pi transit time. You can write it 1 over 2 pi. What was the transit time? It is some distance, let's say gate distance or channel distance divided by V sat. So this particular distance is also going to matter. Why? Because let's see, mm, if let's say for example the electrons are going through a distance like this compared to that of the electrons going to a distance like this, if this is a gate here, this is drain here, let's say this is drain, and in another configuration we have a drain here and the gate at same position, then in this particular case the drain is going to have the impact on the channel, much more impact on the channel. It is going to control the channel, and then that means it's going to have the effect on GM as well. If it's having the effect on the GM, then it's going to have the effect on the frequency, because frequency and GM are basically related. There is a relationship between the frequency and the GM. I don't exactly know how it's derived, but where was it? Yeah, this one. So yes, there is basically if the frequency is GM divided by CGS, 2 pi CGS. And how it arises, because at let's say if you have I out divided by I in, which is the gain, current gain, I out divided by I in, you can write it as I out over I in, not I in. You can use chain rule. No, yeah, that's not the chain rule here. I out divided by V in into V in divided by V into divided by I in. So then you can write this particular thing as GM multiplied by this, you can write in terms of 1 over j omega CGS. Okay, just basically the you can write it in terms of V in divided by I in, and and you know at F equals to current gain frequency, I out by I in is equivalent to 1. That means if we only take the magnitude, that means Gm divided by j omega CGS equals to 1. If you take only the magnitude, then you can write Gm equals to omega CGS. That means omega will be equivalent to Gm over CGS. That means frequency, not new. Let me write F is Gm over 2 pi CGS. So that is where the derivation comes from. And it will directly is going to impact the unity gain, no, unity gain frequency. I sometimes called as unity gain frequency. Unity gain frequency. I hope these are the same things, because at this particular frequency, I in by I out equals to unity. That means you have the unity gain, and it's the current gain frequency. Hmm. That means if this is gain, this is frequency, it will drop like this, and this is the particular value of frequency at which gain equals to 0. Hmm. This is decibels. In decibels, that means log 10 of 0, and why am I messing it up? In decibel, you have 10 log to the base 10 P2 divided by let's call it P2. P2 by P1. When you compare it in decibels, you have the ratio of two different power levels. You do the comparison in terms of the decibels, and whenever the in dB it becomes equivalent to 0, that means you have the I out divided by I in to be equivalent to 1. Okay, so you have log of 10 what is it, 0. That means you can write it 10 to the power 0, you can write it 1 on the other side. Messing it out? No. What is happening? This is 20 dB per decade. Yeah, that is the correct. Gain will be 0 dB. That means 0 dB is 10 log some, let's say P. 10 to the power 0 will be equivalent to P. This is gain. This will be equivalent to 1. So I2 by I1 will be 1. That is what this basically means. I guess I'm exhausted now because it's 2.5 hours I've been teaching now. Uh, okay, now what else we have? Now let me jump to this point because these are material aspects, and let me jump to this particular point. So this particular figure shows how you can extract the maximum power from a field effect transistor. Let's need some water. So if you have a, this is basically the output characteristics of a device. This is ID versus VDS, and you have it increasing and then saturating. And the reason we talked about. Now, what this particular thing is showing is that your drain to source voltage should not go beyond this value, otherwise it will create a breakdown. And it should not be below this value, otherwise it will be in linear region. You want it to be in this region, which is the saturation region. This region. Okay. You want it all together to be in this particular region, so that it is in the saturation region and it should act like the amplifier you want it to act. Now, what is going to happen? And also the current swing, which is this particular thing, it should not be beyond the particular this value, and it should not be minimum here. You definitely you don't want to current to go below this value, otherwise current will become zero, and you don't want the current to become to overshoot this particular value, otherwise it will create breakdown. So that's why what you do, you create something called as bias point. You want them to be exactly in the middle, ideally. What is my middle? You want them to swing around this value. You want them to oscillate around this value only, because if the point is around this and it will swing around here, it will be huge in this side, and on the bottom side, let's not draw it like this, it will be oscillating like this, and on the bottom side this part will get clipped. It will be like this, so this part will get clipped because it's in linear region. Similarly, if you bias it, let's say lower here, then what is going to happen, it will oscillate and this part will get clipped. Okay, then you will have clipping of those waveforms. So that's what you don't want to. You want them to bias exactly at a point, which is called as Q point. It's called as bias point. Biasing means, you want to operate this device at this particular point. Okay, you have to choose something called as, you have to choose a particular point on this output characteristic where you don't want your output characteristic to deviate. You don't want your output waveforms to clip, cut, or distort. So that is the biasing point. Okay. So this Q point is basically Q point as a function of IDS, comma VDS. ID or IDS VDS. Okay, yes. This is a very important factor, I should say. And there is a relation that the maximum power you can get out is basically dependent upon Vmax and Vmin, where this is the Vmax is the breakdown voltage, this is the Vmax, and this is the Vmin, which is the VD sat, saturation voltage. Okay. And then if you have everything, you can basically solve this particular question. You are given breakdown, you are given knee voltage, which is the VD sat, and then you can compute the maximum RF output which you can get from this device will be 1 over 8, 68 minus 4. Is there anything else? No. Then you can have 64 over 8, have 8 watts per millimeter. Is it the answer of this question? Yeah, that is the answer of this question. And where does this 8 come from? That is a different story. You basically have to time average this sine omega t function. Here you have sine omega t function. If you have a current as a sine omega t function, you have voltage as sine omega t function, and when you time average them, you have a 1 by root square somewhere that exactly becomes 1 by 2. So you will be having three factors of 1 by 2, 1 by 2, and 1 by 2 from the current. So that is basically where these particular things come from. And I guess somewhat you can write it as sine omega square t dt. This is sine of omega t. Let me not confuse you right now because you might not be getting this particular thing in here. So there is something called as time average, and there is something called as statistical average. These are two different things. Maybe you might look what these things mean because they are very important quantities in, uh, I should say, all of the signal processing stuff. And that is the end of this session. So we're done. I think we have overshooted to our 2 hour 30 minutes, but it's very difficult to cover everything in whatever the professor has taught in the week in this particular lecture because we cannot directly jump to the questions. Okay, so I guess if you have any question, you can stay. Otherwise, I'm going to stop the recording. Thank you.